In 1935, Albert Einstein sat down at the Institute for Advanced Study in Princeton, New Jersey, and wrote a paper that accidentally predicted a hidden connection through the fabric of space-time. He wasn't trying to invent interstellar travel. He wasn't even thinking about space travel at all. He was trying to fix a math problem. And for decades, that prediction remained a mathematical feature of the equations, something physicists could write down on paper but never test, touch, or build. Then in November 2022, a research team from Google and Caltech published a paper on the cover of Nature, one of the most prestigious scientific journals on the planet, claiming they had observed wormhole dynamics using a quantum computer chip sitting inside a lab in Santa Barbara, California. The headlines went wild. Scientists create a wormhole. Physicists open portal to another dimension. The internet collectively lost its mind. But here's where it gets complicated, because half the physics community celebrated this as a genuine breakthrough in quantum gravity research, while the other half called it, and I'm paraphrasing actual physicists here, a publicity stunt. So what actually happened inside that lab? Did scientists really find a wormhole? Or did the hype machine get way ahead of the actual science? To answer that, we need to go all the way back to where this story begins. And it begins with the most famous physicist who ever lived. The year is 1935, and Albert Einstein is working at the Institute for Advanced Study in Princeton alongside his colleague Nathan Rosen. Together they publish a paper in the journal Physical Review titled "The Particle Problem in the General Theory of Relativity." Their goal is pretty straightforward. General relativity, Einstein's own masterpiece from 1915, keeps producing something called singularities. These are points where the math spits out infinities. And that's a problem because infinity is not a physical measurement you can point to in the real world. It means your equations are breaking down. It means something is wrong, or at the very least something is missing. So Einstein and Rosen take the Schwarzschild solution, which is the simplest equation describing a black hole, first derived by Carl Schwarzschild in 1916 while serving on the front lines of World War I. They extend it using a different coordinate description, looking at it from a new mathematical angle. And when they do, something unexpected falls out of the math. They find a geometric structure, a bridge connecting two separate sheets of space-time, two entirely different regions of the universe linked by a tunnel winding through the geometry itself. This is the Einstein-Rosen bridge, the first mathematical wormhole ever described. Now, Einstein doesn't call it a wormhole. That name comes later from a physicist named John Archibald Wheeler. Wheeler was one of the most creative minds in 20th century physics, the guy who also popularized the term black hole. His notebooks show he first wrote down the word wormhole on November 13, 1955, and he formalized the term in his late 1950s work with Charles Meissner. In that paper, he described what mathematicians would call a handle of multiply connected space, and what physicists might be excused for more vividly calling a wormhole. Wheeler imagined that at the smallest possible scale, about 10 to the negative 35 meters, far smaller than any atom or proton, the smooth fabric of space-time would dissolve into a churning quantum foam filled with tiny wormholes popping in and out of existence constantly. There's just one massive problem with Einstein's bridge: you can't actually use it. In 1962, Wheeler and his colleague Robert Fuller proved mathematically that Schwarzschild wormholes collapse so quickly that nothing can traverse them. Not a spaceship, not a radio signal, not even a single photon. The bridge forms and collapses in the same instant. So for decades, wormholes were a beautiful mathematical curiosity and nothing more. A door that existed on paper but slammed shut the instant you tried to walk through it. And that's where the story might have ended, except that a science fiction novel changed everything. In 1985, the astronomer Carl Sagan was finishing his novel Contact and needed his main character, an astrophysicist named Ellie Arroway, to travel across the galaxy fast. He originally had her fall through a black hole, but Sagan cared about scientific accuracy, so he sent his manuscript to his friend Kip Thorne, a theoretical physicist working at Caltech in Pasadena, California. Thorne read the draft and told Sagan that a black hole wouldn't work. The tidal forces would rip the character apart long before she reached the other side. He suggested a wormhole instead. And then Thorne did something remarkable. He didn't just wave his hands and say, sure, wormholes could work. He actually sat down and worked out the physics. He asked the question seriously, in a way nobody had done with full mathematical rigor before. Could a wormhole exist that a human being could safely pass through? The answer, published in 1988 in the American Journal of Physics with his graduate student Michael Morris, was a conditional yes. The Morris-Thorne wormhole was the first mathematically rigorous traversable wormhole ever constructed. They showed it was permitted by general relativity, that a traveler could pass through without being crushed. And in a follow-up paper in Physical Review Letters that same year, Thorne, Morris, and Ove-Yurtsever showed something even more provocative. If you take a traversable wormhole and accelerate one mouth relative to the other, relativistic time dilation kicks in. The two mouths age at different rates, and that means a traversable wormhole could, at least in theory, function as a time machine. You walk in one end in 2026, and you walk out the other end in 2016. Stephen Hawking took this seriously enough that he proposed what he called the chronology protection conjecture, essentially arguing that the laws of physics would conspire to prevent this from ever actually happening, but nobody has proven him right yet either. The catch for all of this is brutal. To hold a wormhole open against collapse, you need something called exotic matter. This is material with negative energy density, material that effectively counteracts gravitational collapse and keeps the wormhole throat from squeezing shut. Now, negative energy sounds like science fiction, but it actually exists. The only experimentally confirmed source comes from something called the Casimir effect. The Dutch physicist Hendrik Casimir predicted this in 1948 while working at the Philips Research Laboratories in the Netherlands, and S.K. Lamoureux confirmed it by experiment in 1997. When you place two uncharged metal plates incredibly close together in a vacuum, quantum fluctuations create a measurable attractive force between them. And in the space between those plates, the energy density drops below that of the surrounding vacuum, effectively creating a region of negative energy relative to the empty space outside. It's real, it's been measured, but the amounts are absurdly tiny. We're talking about forces you need extremely sensitive equipment to even detect. Nowhere close to enough to prop open a tunnel through space-time big enough for anything to pass through. Even Thorne acknowledged this gap. He said, "We have very strong indications that you can never get enough negative energy to keep a wormhole's walls from collapsing." So traversable wormholes went from impossible to theoretically possible but practically impossible. Which is progress, sure, but frustrating progress when you're hoping to build a shortcut to the stars. Now here's where the story takes a turn that nobody saw coming. And this is where it gets really wild. Remember Einstein's 1935 paper about the bridge connecting two regions of space-time? Well, that exact same year, Einstein published another famous paper. This one was written with Boris Podolsky and Nathan Rosen, known as the EPR paper, also published in Physical Review. That paper described quantum entanglement, the phenomenon where two particles become correlated in such a way that measuring one instantly reveals information about the other, regardless of distance, without anything actually being sent between them. You could put one particle on Earth and the other on the far side of the Milky Way galaxy, and the correlations would still hold. No signal travels, no information is transmitted faster than light, but the connection is real and measurable. Einstein hated this. He called it spooky action at a distance, and thought it proved quantum mechanics was incomplete. For nearly 80 years, these two 1935 papers seemed completely unrelated. One was about tunnels through space-time, the other was about spooky quantum correlations. Different physics, different math, different implications, different everything. Then in June 2013, two of the most brilliant theoretical physicists alive connected the dots in a way that made the entire physics world sit up straight. Juan Maldacena, working at the Institute for Advanced Study in Princeton, and Leonard Susskind at Stanford University in California proposed a conjecture so elegant it could fit in 3 characters. ER equals EPR. Wormholes and entanglement may be deeply, fundamentally connected. According to Susskind, Maldacena sent him a cryptic message containing just that equation, and Susskind understood immediately. Their paper, published in Fortschritte der Physik, argued that two entangled black holes are connected by a wormhole. Not metaphorically, not as an analogy. If the conjecture is right, the quantum correlation between entangled particles doesn't just resemble a wormhole connection, it is one. Maldacena described the implications by saying that the solid and reliable structure of space-time exists because of the ghostly features of entanglement. If he's right, the fabric of the universe isn't made of atoms or energy or strings. It's stitched together by quantum entanglement, and wormholes are the seams holding it all together. This conjecture was built on Maldacena's earlier masterwork, the ADS-CFT correspondence, proposed in November 1997 when he was a young faculty member at Harvard University. That paper has been cited over 10,000 times, making it one of the most cited papers in all of high-energy physics. What it showed was mind-bending. A theory of quantum gravity in a higher dimensional space is mathematically equivalent to a quantum theory without gravity on that space's boundary. Think of it like a hologram. A hologram is a flat, two-dimensional piece of film, but when you shine light through it, you see a full three-dimensional image. Maldacena showed that the universe might work the same way. All the information about a three-dimensional volume of space could be encoded on its two-dimensional surface. This is the holographic principle, first proposed by Nobel laureate Gerard de Hooft in 1993 and developed further by Susskind in 1995. This goes beyond metaphor or thought experiment. This is a precise mathematical duality that has passed numerous non-trivial consistency checks over the past 3 decades. And this holographic duality is exactly what the 2022 Google experiment set out to explore. On November 30th, 2022, the journal Nature published Traversable Wormhole Dynamics on a Quantum Processor as its cover story. The research team spanned 5 institutions. Maria Spyropoulou from Caltech served as the principal investigator and corresponding author. Daniel Jafferis from Harvard was the lead theorist. Alexander Zlokapa from MIT was a co-first author who had actually begun the work as an undergraduate at Caltech. Joseph Leiken from Fermilab and Hartmut Neven from Google Quantum AI rounded out the key team members. The experiment used Google's Sycamore quantum processor, the same chip Google had previously used to claim quantum supremacy, but they only used 9 of its 72 available qubits. The quantum system they chose to simulate was something called the Sachdev-Yekitaev model, or SYK model. This is a system of randomly interacting particles first described by Subir Sachdev and Jinwoo Ye in 1993, and later shown by Caltech's Alexei Kitaev in 2015 to have properties that, in certain limits, are dual to a simplified black hole in a two-dimensional universe. Daniel Jafferis, working with Ping Gao and Aaron Wall in 2017, had proved that 2 linked SYK systems could encode a traversable wormhole, so the theoretical foundation was solid. The challenge was that a full SYK model requires hundreds of particle interactions, far too complex for any quantum computer that exists today or will exist in the near future. This is where the experiment got creative. Zlokapa used machine learning to compress the model. He mapped the SYK particle interactions onto neural network connections and used machine learning to build a much simpler model that preserved key features of the dynamics. The result was a dramatic simplification, 210 four-way interaction terms reduced to just 5. 7 qubits were prepared in a special entangled state called a thermofield double, with each qubit on the left side entangled with a partner qubit on the right side. In the gravitational picture provided by holographic duality, this represents 2 black holes connected by a wormhole. A probe qubit's information was injected into the left system, where it scrambled among all left side qubits. Think of this as information falling into the left mouth of the wormhole and getting mixed up with everything inside the black hole. Then, a specific global operation was applied to all qubits, one that, in the dual gravitational picture, corresponds to a negative energy shock wave propping the wormhole open. The information transferred from the left qubits to the right qubits and unscrambled, refocusing at a single point on the right side. John Preskill at Caltech described this unscrambling as chaos run backward. And here's the detail that honestly makes this story feel like a movie. Alexander Zlokapa ran the final successful experiment late one night in January 2022, not from a gleaming research facility, From his childhood bedroom during winter break, remotely accessing the Sycamore quantum processor on his laptop through the internet. He sent a message to Maria Spiropoulou that read, "I think we see a wormhole now." Spiropoulou later said she was shaken when she saw the data, comparing the feeling to the moment she first observed evidence of the Higgs boson in 2012 at the Large Hadron Collider in Geneva, Switzerland. The team reported 5 features they argued were consistent with the expected behavior of a traversable wormhole in the model's gravitational interpretation. Negative energy asymmetry, meaning information successfully transferred with negative energy operations, but failed with positive energy ones, matching what the wormhole interpretation would predict. Perfect size winding, which is a delicate information spreading pattern that appeared spontaneously even though the machine learning algorithm hadn't been trained to produce it. Jaffra said, "They didn't demand anything about this property, but it just popped out." They also observed Shapiro time delay, causal time ordering, and proper scrambling dynamics. All 5 were consistent with what the gravitational dual would predict. But here's the thing, the team was very careful to emphasize, this was not a physical tunnel in our space-time. The wormhole existed within the mathematics of a simplified toy universe, the one described by the holographic dual of the quantum system running on the chip. Jaffra called it a filament of real space-time, but clarified it was not part of the same reality that we and the Sycamore computer inhabit. Spiropoulou described the whole thing as a quantum gravity experiment on a chip. Not everyone bought it. Within hours of publication, prominent physicists launched what became one of the most heated scientific debates in recent memory. Scott Aronson, a quantum computing researcher at the University of Texas at Austin, wrote on his blog that if this experiment brought a wormhole into physical existence, then you also bring a wormhole into existence every time you sketch one with pen and paper on a napkin. He questioned why the standards should be different just because a quantum computer ran the calculation instead of a classical one. Peter Shor at MIT, the mathematician whose algorithm forms the foundation for quantum computing's threat to modern cryptography, said the theory tested only has a very tangential relationship to any possible theories of quantum gravity in our actual universe. Matt Strassler at Harvard went further, saying it's not the real thing and it's not even close to the real thing. Sabine Hossenfelder, a physicist and popular YouTube creator, called the headlines nonsense and pointed out that using the same mathematical framework, pouring water into your kitchen sink qualifies as a black hole. The sharpest scientific challenge arrived in February 2023. A team led by Norman Yao at Harvard, along with Bryce Coburn and Thomas Schuster, published an analysis on the scientific preprint server ER EPR. Their finding posed a serious challenge to the original interpretation. The simplified model's 5 remaining interaction terms all commuted with each other. In plain language, that means the system lacked the chaotic scrambling behavior that genuine holographic gravity requires. The perfect size winding that Jaffra and the team had celebrated as spontaneous evidence of gravitational behavior wasn't special at all. It was just a generic property of small, simple quantum systems with commuting terms. 5 independent experts consulted by Quantum Magazine agreed the analysis seriously challenged the experiment's gravitational interpretation. Even John Preskill, who had initially praised the work enthusiastically, updated his assessment. He said the evidence for a gravitational interpretation was weakening. The media handling drew its own criticism. The paper had been kept off arXiv before publication, which is unusual in physics where preprints are the norm. It was distributed under embargo to select journalists and accompanied by coordinated press releases from multiple institutions. Columbia University mathematician Peter Woit, writing on his blog Not Even Wrong, called the whole affair a publicity stunt that overstepped the actual science. So was the experiment a waste? No. And this is where the story gets really interesting. What the controversy clarified was not that the experiment failed, but where the real frontier lies. The experiment used 9 qubits, a system small enough to simulate classically with modest computing resources. The quantum computer didn't teach us anything a classical computer couldn't have confirmed. For quantum gravity experiments to produce genuinely new physics, scientists need systems with 100 or more qubits running non-commuting interactions that preserve chaotic scrambling. That's the actual benchmark. and quantum hardware is advancing toward that threshold faster than anyone expected, even 5 years ago. Meanwhile, the theoretical side of wormhole research has been on fire since 2022. Juan Maldacena, together with Alexei Malekin and Fedor Popov, published a solution in classical and quantum gravity in 2023 for a four-dimensional traversable wormhole that requires no exotic matter in the traditional sense. The Maldacena-Malekin-Popov wormhole relies on carefully arranged quantum effects involving charged massless fermions and magnetic fields to generate the negative Casimir-like energy needed to hold the wormhole open. It only works under highly constrained conditions, and at scales far smaller than anything we could practically use, way below the electroweak scale. And nobody is claiming you could build one of these in a lab anytime soon. But the theoretical significance is real. For the first time, someone constructed a traversable wormhole solution without inventing speculative new physics from scratch. The ingredients, at least in principle, come from the physics we already understand. And in November 2025, physicists Rajdeep Mondal and Abhishek Sadhukan studied what gravitational wave signatures this type of wormhole might produce and found something intriguing. A traversable wormhole could, in principle, create a distinctive echo pattern in gravitational wave data, a fingerprint different from what a black hole produces when it rings down after a collision. That means observatories like LIGO in Livingston, Louisiana, the Virgo detector in Cassina, Italy, and the Kagra detector in Kamioka, Japan, might eventually be able to look for wormhole signatures. Not by building one, but by listening for their echoes in the vibrations of space-time itself. Imagine two massive objects colliding somewhere in the cosmos, merging in a cataclysmic event that shakes the fabric of the universe. LIGO detects the gravitational waves rippling outward. If one of those objects behaved like a wormhole instead of a black hole, the ring-down signal would show extra pulses, echoes bouncing through the wormhole throat. Detecting and interpreting such signals remains hugely uncertain, and nobody has found a confirmed signature yet. But the detectors are running, the theoretical predictions are sharpening, and the sensitivity keeps improving with every upgrade. On the ER equals EPR front, a March 2025 paper by Ning Bao at Northeastern University and Grant Remen at New York University, honored by the Gravity Research Foundation, provided new mathematical evidence supporting one direction of Maldacena and Suskind's original conjecture, showing that wormholes sharing an exterior space-time must also share quantum entanglement. And a December 2025 paper proposed testing the conjecture by examining the hyperfine structure of hydrogen atoms. The idea is that if entangled particles really are connected by microscopic wormholes, there could be a tiny effect on how the proton and electron interact inside ordinary hydrogen. This remains purely theoretical, and any such effect would be extraordinarily small. But precision atomic measurements are already pushing the bounds of what we can test, which is exciting on its own. Wormholes have also become essential for solving one of the biggest unsolved mysteries in physics: the black hole information paradox. When a black hole evaporates over billions of years through Hawking radiation, named after Stephen Hawking, who predicted it in 1974, what happens to all the information about everything that fell in? Quantum mechanics says information can never be destroyed, but the radiation streaming off the black hole appears to be nearly random thermal noise with no obvious way to recover the information that went in. That's a direct contradiction, and physicists have been arguing about it for 50 years. In 2019 and 2020, a series of breakthrough papers by Ahmed Almheri, Thomas Hartman, Maldacena, and others showed that wormhole-like structures called replica wormholes, appearing in the gravitational path integral, can actually recover the missing information. The math produces what is called the page curve, which is the specific pattern information recovery should follow if quantum mechanics is right. Physicist Kanado Goto at Riken in Japan explained that they discovered a new space-time geometry with a wormhole structure that had been overlooked in conventional calculations, and that the entropy computed using this geometry gives a completely different result from what everyone had assumed. So where does all of this leave us? The 2022 experiment did not create a wormhole. The critics were right about that. But dismissing it entirely misses the bigger picture, what the experiment demonstrated, And what the backlash helped sharpen is that quantum computers may eventually be able to simulate gravitational systems that no classical computer can handle. And those simulations could reveal physics about quantum gravity that mathematics alone can't access. The real story here isn't about building tunnels through space. It's about answering the deepest question in all of physics. How do quantum mechanics and gravity become the same theory? Because right now, those two pillars of modern science are fundamentally incompatible. General relativity describes gravity as the curvature of space-time, bending and warping around massive objects like stars and black holes. Quantum mechanics describes everything else as particles and probability waves. For over a century, the smartest people alive have tried and failed to make them agree, and the consequences of that failure are real. We can't describe what happens at the center of a black hole. We can't explain the first instant of the Big Bang. We can't build a complete theory of how the universe works, because our two best theories contradict each other at the most fundamental level. Wormholes have quietly emerged as one of the most promising ideas for connecting those two worlds. ER equals EPR suggests that space-time itself is woven from quantum entanglement. The holographic principle implies that our three-dimensional universe might be encoded on a two-dimensional boundary. Traversable wormhole solutions suggest that tunnels through space-time may be compatible with the physics we already understand. And gravitational wave observatories might soon be able to detect their signatures. As Daniel Jafferis explained, he believes that gravity in our universe is emergent from quantum bits, in the same way that the little baby one-dimensional wormhole in their experiment was emergent from qubits on the Sycamore chip. He added that of course they don't know that for sure yet. They're still trying to understand it. We haven't found a wormhole, not yet. But we're closer than we've ever been to understanding whether the universe has been hiding shortcuts in its fabric all along. And the wildest part of this entire saga might be that a graduate student in his childhood bedroom on a laptop may have caught the very first glimpse of one. If you're finding this as mind-blowing as I do, hit subscribe. I cover the biggest breakthroughs in space and science every week, and trust me, the next one is going to be just as wild. I'll see you there.